Alright, welcome back. This is video I3, and we left off on problem 1G. I don't know why I just didn't number all these. Let's call this problem 2, make it simpler. Alright, so now we have the limit as x goes to 0 from the right of the square root of x times the natural log of x. And with each of these functions, you can probably understand why we're choosing just a one-sided limit. Alright, so go with your instinct, see what you get. Okay, as x goes to 0 from the right, the square root function goes to 0. But the natural log function, don't forget what the graph looks like. It goes off to negative infinity. And we've talked about this. This is definitely an indeterminate form, but it is not one of the ones we're looking for. So just as we did in a previous problem, we have to try to express this as a fraction in order to get one of the good indeterminate forms. So instead of multiplying by that, I'll divide by its reciprocal, forcing there to be a fraction. Okay, and now see what we get. We have, as before, negative infinity over infinity, and that's definitely one of our good indeterminate forms. So we're going to take the derivative of the top and the bottom. So I have, this is equivalent to the limit as x goes to 0 from the right. The derivative of the top, remember this is x to the negative 1/2. So I took its derivative. Okay, clean that up a little bit. Divided by this is the same thing as multiplying by negative 2. This is x to the negative 1. I'll subtract negative 3/2, so I have negative 2/2 plus 3/2. I just get that. And so this goes to 0. I get negative 2 times 0, which is 0. Okay, problem 3, maybe a little trickier. Once again, a one-sided limit, but we're not given a fraction. We're given the difference of two fractions. Okay, we could check this out. Let's see if it's an indeterminate form. So I have basically infinity minus infinity. And that definitely is indeterminate. We don't know which of these is going off to infinity more quickly. Okay, so it's indeterminate, but it's not one of the good forms. And so simply rewrite this as one fraction by getting a common denominator. Okay, and so I'll write my limit again. Remember, you have to do that every time. Okay, and then my common denominator will be x times the sine of x. And so I get x minus sine x over x sine x. And once again, we'll try to apply the limit. I'll get 0 minus 0 on top, and on the bottom I get 0 times 0, and now we have a good indeterminate form. I'm trying to save space here because this is going to be kind of a big problem. So I'll go ahead and apply L'Hopital's. I have to remember I need to write my limit each time. The derivative of the top, term by term, with respect to x, is that. The bottom is the product rule, so I have the first times the derivative of the second minus the second times the derivative of the first, which is 1. So we might as well see if this is now going to, if we can evaluate it or if we'll have to continue. And so I would get 1 minus 1, so I'll get a 0 on top. On the bottom, that, since I'm multiplying by 0, is 0. This is 0. And so I, once again, get a good indeterminate form. We've done this before. So we'll continue by now applying L'Hopital's to this step. So I have the limit as x goes to 0 from the right. The derivative of the constant is 0. Derivative of cosine is negative sine, but I have a negative out there already. Once again, a product rule, so first times derivative of second, or plus second times derivative of first. And then the derivative of this term is going to be, I feel like I messed up somewhere. Oh, that was a plus for the product rule. Anyway, so I have the derivative of sine x here, which is cosine x, all on the bottom. Okay, and so let's go ahead and try to apply the limit now. Up top, sine of 0 is 0. That term is 0 on the bottom, but these are each 1. And so I get my limit is 0. So this function, as x approaches 0 from the right, would be approaching 0. Okay, so now I have quite a difficult problem. Okay, this is the big problem of this section. Problem 4. Let's find the limit as x goes to 0 from the right of 1 plus x to the 1 over x. Okay, and so go ahead and try to apply the limit. And I get 1 plus 0. So 1 to the infinity. And we've talked about that. This isn't exactly 1, it's approaching 1. This is an infinity, of course, it's approaching infinity. And the rate at which we're approaching both may impact the value of the function, the entire function, as x gets close to 0. Okay, so this is an indeterminate form, but clearly it's not a fraction. Okay, and so I want you to remember, on this problem, this is the key to this. I'm going to always say when we get anything like this the rest of the year, this is a messed up exponent. And so we have to somehow get rid of exponents, and you guys already know a trick for getting rid of exponents. And it goes like this. I'm going to let f of x equal this side. So my entire goal is to find the limit of this, so I'm looking for the limit of f of x. Okay. But we talked about how we don't want this messed up exponent, and to get rid of it, what I'm going to do before I apply a limit here is I'm going to take the natural log of both sides of this equation. So the natural log of f of x is equal to the natural log of 1 plus x to the 1 over x. And you guys have learned your exponent or your logarithmic properties. If you have an exponent, you can bring it out front as a coefficient. And that out front as a coefficient would be equivalent to that. And all of a sudden, I have a fraction on the side. That's always our goal, to get a fraction so we can apply L'Hopital's to these. Okay, so at this step, remember my goal is to find the limit of f of x. So I'm going to take the limit of both sides. Okay, now I've taught you something this year, and it's key. We use it in a number of ways. But this is a limit of a composition of functions. And I think I need one more little set of parentheses in there. Okay, this is the inside function, and we have this theorem that allows us to take the limit of the inside function and then apply that function to it. In other words, it looks like the natural log is popping out in front of the limit. Once again, one more set of parentheses. Okay, on this side, maybe I should try it right here since I have space. Okay, I'm going to see if I can actually evaluate this limit now. So I have, as x goes to 0, the natural log of 1. So we have to remember what the natural log of 1 is. And then as x goes to 0, it's 0. And so this is definitely set up for L'Hopital's, our entire goal here. Okay, so then rewrite your limit. Take the derivative of the top And the derivative of the natural log of something is 1 over that something times a chain, but the chain would just be 1, so we don't have to do that. And on the bottom, the derivative of that is just 1, and this looks like we can evaluate it. And so let's go ahead and write this step here. So remember, our entire goal is to isolate that. Over here, I just get 1. So to isolate this now, this is just a natural log. So I'm going to do the log circle. My base is e. Circle the base, go across, and come back. And I get the limit as x goes to infinity, or from 0 to the right, of f of x equals e to the first. And so maybe you recognize that right from the beginning, I've given you this definition of e before. Okay, so the only problem we'll do tomorrow as a class will be this next problem. I'll give it to you right now, and I want you to work with it and see if you can evaluate it. This is problem number 5. I want you to try to find, as homework tonight, that limit. That's x to the 1 over x. Good luck.